An important concept in molecular orbital theory is the concept of orbital overlap. And this can be quantified in something called an overlap integral, which is symbolized as an S. So let's just look at an overlap integral of two different atomic orbitals. So atomic orbital mu and atomic orbital nu. We can define S nu as this integral of these two functions over all space, which in bracket notation looks like that. So let's just draw out what we mean by this overlap integral by looking at two S functions. So we're going to draw this out as a two-dimensional function first. We're going to put nucleus mu here and nucleus nu here. So mu looks like that, nu looks like that, and your overlap is in that region there. So that is your overlap integral. Another way we can look at this is that we can have an overlapping S function mu and nu with that area there corresponding to that area there. So this is a pictorial way of representing this overlap integral. What we did here is we looked at the overlap of two symmetry-related wave functions with the same sign. So we took an in-phase function and an in-phase function, both with positive signs associated with them. We could have taken our function and put negative signs on them. And we would have gotten the same result back. So here, what we're doing is we're taking the overlap of this. We can take the scalar out of the integral. So we're just taking -1 squared. And that's equivalent to this. So mathematically speaking, these two representations are identical to one another. The phases are the same, so the overlap integral is going to be the same. If we look at the out-of-phase combination, which would correspond to an antibonding interaction, then now the overlap integral is this, taking out the scalar, we get this, which is equal to negative S nu. So the overlap for an antibonding combination is the same as the bonding combination, only it has the opposite sign. We can define bonds based on the overlap geometry. So we've talked about sigma and pi bonds. We've introduced delta bonds. So we're just going to formally define them here. So a sigma bond is any bond that's symmetric with respect to rotation, about the bonding axis. And these come from combinations such as an S plus an S plus a P in that orientation, a P plus a P in that orientation, a D plus an S, a D plus a P, and so on and so forth. A pi bond is antisymmetric with respect to a C2 rotation. So this can result in a p orbital and a p orbital, a p orbital and a d orbital, a d orbital and a d orbital, overlapping like that, and etc. A delta bond is antisymmetric with respect to a C4 rotation, but symmetric with respect to a C2. And these generally result from, for example, a d orbital overlapping with a d orbital in this type of fashion, where this lobe overlaps here, this lobe overlaps here, this lobe here, and this lobe here. In general, the overlap integral decreases going from a sigma type bond to a pi type bond to a delta type bond. So overlap integrals are largest for sigmas, smaller for pi's, and even smaller in magnitude for delta bonds. We're now going to start talking about the dependence of this overlap integral on distance of the two orbital fragments from one another, as well as their geometric orientation relative to one another. So the overlap integral is made up of two parts. One depends on the type of interaction as a function of distance, and the other depends on an angular parameter in terms of two bond angles. So first, we're going to look at the dependence of R given equivalent values of our angular parameter on the overlap of two s orbitals, two p orbitals, and an s and a p orbital. So we're going to look at the magnitude of s versus distance. And if we look at the overlap of two s orbitals, so just to give us an idea of what we're looking at here, we're talking about bringing two s orbitals from overlapping and then bringing them out to some faraway distance. So what happens is this overlap integral goes from 1 and then decays down, eventually reaching 0 at infinity. Reason it goes up to 1 is because as we bring this in, you get complete overlap of those two. Then the overlap decreases as you go out. We can also look at p-type combinations. Where we're bringing this p orbital here from 0 and then bringing it out like that. Okay. So this starts off as 1, but then rapidly decays relative to the SS combination. Okay. So you can see that with the S overlap, you have a large overlap as we bring that off, and then it decays slowly out. However, because of the nature of the p-type interactions, we have a large overlap because they're directly over top of each other, but that's going to rapidly decay because of the diffuseness of that orbital as you go out. We can now look at the overlap of an S and a P function in a sigma-type manner. So we'll have our S orbital and our p orbital. We're going to be bringing this from an overlap of 0 all the way to some distance far away. And you can see when it's at 0, so it's over top of that other nucleus, that s orbital is sitting on a node. As we bring it out, it's going to overlap, we're going to reach some maximal overlap, and then it's going to decay. So for an SP combination, your overlap interval goes from 0, reaches some maximum value, and then decays back down at further distance. If you notice, we never reach as high of a value as we do with an SS combination. Just as important as distance is this angular component. So if we're looking at two s orbitals, so s, s, and we're going to look at some bond angle going from 0 here to about 90 degrees. If we look at the overlap integral over its maximum possible value for that SS overlap integral, we're going to see that it remains constant as we go across, because no matter how you're oriented, there's always going to be overlap in that sphere. It's spherically symmetric. Things change, however, when we look at overlap of orbitals that are different than s. So for example, if we look at an SP overlap divided by the maximum possible that this particular overlap integral can be, so that would be 1. What we're doing is we're going to look at that value of theta there, going out to 90 degrees from 0 degrees. It has a maximum value at a theta of 0, and then it goes to 0 at 90 degrees. So as you change this bond angle, you're changing the overlap between those orbitals. Or another way of saying this is that when the s orbital is in the node of the p orbital, there's 0 overlap. We can look at PP combination over a maximum possible value of 1, going from 0 to 90 degrees here. There's your theta value. At a value of 0, this orbital is here. So this phase here is in this nodal structure. So it has an overlap of 0. But as you go to 90 degrees, you reach the maximum possible overlap. So it goes something like that. And as one last example, we're going to look at an SD overlap over its maximum possible value. and here. There's your value of theta. At 0 degrees, it sits in a node. Here, at 90 degrees, it sits in another node, but it's at its maximum overlap at 45 degrees. So the overlap integral goes like that, with that maximum being at 45 degrees. These overlap integrals are incredibly important because it signifies both the energy of your resulting molecular orbital. Also, it signifies how much mixing of the two orbitals you're going to have. So how much of one orbital is going to contribute to the overall molecular orbital upon formation. I'm going to skip a huge amount of derivation here and just go directly to the answer. But let's say we have two orbitals that we're looking at, mu and nu, and they're separated by some energy. And we'll just call those energies E1 naught and E2 naught. Those are the energies of the individual orbitals that we're going to be overlapping. So we know that these will form antibonding and bonding combinations. Like that. And we're going to give these energies E1 and E2. It turns out that these energies here are directly related to the overlap integral of these two wave functions. I'm going to write the form for E1 just so you can see how this overlap integral comes into play. I have to define another integral. This is H12, which is your interaction integral. So it's telling you how the two wave functions are coupled together through that Hamiltonian operator. And E1 is just equal to E1 naught minus H12 minus E1 naught S12 squared all over E1 naught minus E2 naught. Now here, this H12 is a negative term, so we're lowering the energy of this, which is stabilizing the energy relative to the atomic orbital. So the larger the value of your overlap integral, the more stabilized the energy of the resulting molecular orbital is going to be. Furthermore, the coefficients that are making up that particular molecular orbital, C1, depend on that overlap integral. Without going into any type of detail, I'm going to write a quantity T, which is just equal to H12 minus E1 naught S12 over E1 naught minus E2 naught. This wave function is going to be proportional to 1 minus T S12 minus 1/2 T squared V1 plus T V2. So this overlap integral is also playing into these coefficients here. In essence, the smaller this overlap integral is, the more that this wave function here is going to play into the overall molecular orbital. So the key takeaways are that these overlap integrals, which describe the amount of overlap of the two wave functions making up a particular molecular orbital, is important because it dictates both energies of your resulting molecular orbitals, as well as how much atomic orbital character of each function that's mixing in is contained in that molecular orbital. So as S goes up, your energies become more stabilized for your bonding. The energy goes more destabilized for the anti-bonding orbital. And also, the atomic orbitals become more evenly distributed in the molecular orbital. So the atomic orbitals become more represented in the molecular orbital. The factors that influence your overlap integral include your type of orientation, so essentially the type of bond that you're forming, with sigma bonds having larger overlap integrals than pi bonds, which have larger overlap integrals than delta bonds. The distance dependence, so how far apart your nuclei are going to influence how much overlap you're going to have from the wave functions. And also your angular orientation. Are those two orbitals meeting head on, or is one in a node relative to the other?